Welcome back. In this video, we are going to solve example 5.28 that is taken from Mechanics of Material by Beer and Johnston, 6th edition. Statement is determine the distance A for which absolute value of bending moment in the beam is as small as possible, and in part B the corresponding maximum normal stress due to bending. So you can see this is beam clear that is having fixed support at point A, and at point C there are roller support. At point B there is a hinge and there is a uniformly distributed load of 4 kips per feet. The total length is 18. So you have to determine this distance A for which the absolute value of bending moment in the beam is as small as possible. So let's start with the solution. So you can see that this total length is 18 and this distance is A. So this remaining distance will be equal to, let this distance will be equal to B, and this B will be equal to 18 minus A. So I can write it, let B is equal to 18 minus A. And also given that this beam is wide flange beam, which is W 14 by 68. So now you can see there is a hinge at this point B, clear. So what we do is that we will remove this hinge and we will take segment BC. So I will write segment BC. For segment BC, I have to draw the free body diagram of this beam. So this is your point C. At C, when you remove this roller support here, so you will be having a normal reaction force. Let this normal reaction force is represented as C, clear? Or you can also write it as Cy, okay? And there is a uniformly distributed load till this point C. So I will draw it the uniformly distributed load as well. And its magnitude is 4 kips per feet. This is your point B. Now at point B, when you remove this hinge, so there will be a vertical reaction force that will act on this point B, and let this reaction force is represented as VB, or you can also write it as By, but I am taking here as VB. You can take anyone. And the total length of this segment BC is represented as B, and this B is equal to 18 minus A. Now what we will do is that we will find this VB and Cy by using equation of equilibrium. So first equation of equilibrium is that sum of all moments about point C is equal to 0. Okay. So taking the counterclockwise movement as positive. So about point C, the first movement is due to this VB load and perpendicular distance is B, and this is producing clockwise movement, so it will be negative. So I can write VB multiplied by this B, and that is negative. The second load is due to this uniformly distributed load, and when this load is converted into a point load, so it will be 4 multiplied by the length over which it acts, which is B, and that will act at a distance of B by 2 from the both sides. So I can write it B by 2. And due to this load, the moment at point C will be counterclockwise and perpendicular distance will be B by 2, and it will be positive moment. So I can write plus 4 times B into B by 2 is equal to 0. So what we will do is that VB multiplied by this distance B is equal to 4. 2 will cancel with this 4. So I can write it as 2B square. Sorry, yes, 2B square. So I can write it 2B square. So from here, this VB reaction force at point B will be equal to 2 times B. And same, now you can find this Cy by using equation of equilibrium, that sum of all forces along y direction must be equal to 0, and upward force is taken as positive. So VB, which is upward, and VB is 2b minus this 4b plus cy is equal to 0. So from here you will get cy will be also equal to 2b. So these are the reaction force. Now what we are going to do is that we will section this segment BC at any length and we will take this distance as x, clear, and we will find the bending moment equation for this segment. So what I am going to do is that I will choose another color, green color, and let we cut this beam at a distance of x from point B. So when you cut it, so you will be having free body diagram will be like this. So this was your VB, clear. There is a distributed load over the length of x. This is x, clear, and this distributed load is downward. Okay, so when you cut it, so definitely you know that you have a shear force here. Let this shear force is V, and you have a moment M as well. And we take this point as point J. Okay, now we'll find this moment M by using equation of equilibrium. So first the equation of equilibrium that we will be using is sum of all moment about point J is equal to 0, and taking the counterclockwise moment as positive. So first moment about point J is this VB multiplied by this distance x. So I can write VB multiplied by this distance x. Now this uniformly distributed load, which is 4 kips per feet, and when converted into a point load, so this will be equal to 4 times this x, and that will act at a distance of x by 2 from either side. So the moment that is produced by this 4x into perpendicular distance x by 2, and this is producing counterclockwise moment, so it will be positive and this will be negative. Their sum must be equal to 0. So from here this VB multiplied by x is equal to, okay, one more thing I have left is that there is another moment as well which we are going to find, that is external moment, that is also counterclockwise, so their sum must be equal to 0. Now this moment will be equal to VB multiplied by x minus 4x square over 2, and we know that VB is equal to 2b, so 2b into x minus 2x square, and the unit of this moment will be pound into feet. So we have find out this equation of moment for segment BC. Okay, so let me write it, 2bx minus 2x square, unit is pound into feet. Let this is your equation number 1, and this equation 1 is bending moment equation for segment BC. Now what we are going to do is that if I draw this segment BC again, let me copy all these things. Let me copy it and I will paste it over here. Okay. I will make a copy of this. Okay. Now I will paste it over here. So you can see this is the beam. And if I draw the bending moment diagram for this, I will draw a vertical line from the both end of this beam and then a horizontal line to show the length in x in feet. Okay, here you have bending moment. We are not taking the shear force because we are concerned with the moment. Okay, now put x is equal to 0 in equation 1. So you will get, you know that this x will be 0 and this will be 0, so moment will be 0. moment is equal to 0. Okay, and for x is equal to how much? X is equal to, let me show you here, x is equal to 18 minus a, or x is equal to b. Okay, at x is equal to b, b is this one. So you can see moment will be equal to, put in equation 1. So moment will be equal to 2b multiplied by b minus 2b square. So 2b square minus 2b square will be 0. So it means at both at the start and end of the beam the moment is 0. Now we are going to find out the maximum bending moment. So for maximum bending moment, I will write it. For maximum bending moment, we need xm, which is the location where the bending moment, maximum bending moment will occur. So what we will do is that we will take derivative of that moment with respect to x. So I can write d over dx, and the equation of moment was 2bx minus 2x square. So when you take the derivative of first, so it will be 2b minus the second one will be equal to this 2, this will be 2b minus 2 into 2 minus 4x. Okay, so dm over dx will be equal to 2b minus 4 times, and for you are going to find out x, that will be xm. Now this dm over dx must be equal to 0 in order to find this xm. So what we will do is that we will take it 2b minus 4xm. So 4xm is equal to 2b, and xm will be equal to 2b by 4, and that will be equal to b by 2. So what we get is that xm is equal to b divided by 2. So put the value of this, put xm is equal to b divided by 2 in equation number 1. This is your equation number 1. So what you will get is that m is equal to 2b multiplied by x will be equal to b divided by 2 minus 2 times b divided by 2 whole square. So we will get 2, we will get 2 will cancel. So we will get b square minus 2b square over 4. So that will be b square minus b square over 2. And that moment will be equal to b square over 2. This moment will be the maximum bending moment. Now we will let this point is your midpoint, and at this point you have b square over 2, which will be the maximum bending moment. Okay, so your bending moment will be a curve like this. Why? Because you can see that this load is uniformly load, so its shear force will be 1 degree line, and bending moment will be a 2nd degree line. Also you can see this equation is a quadratic equation, so it will be a like curve. So for segment B we will get maximum bending moment is equal to b square over 2 for segment BC. Now what we will do is that I will choose blue color. Now for segment AB, so let me show you, this is your segment AB. So when you remove this this is your segment AB, and having uniformly distributed load like this, which is equal to 4 kip per feet, and this length is A. So when you remove this fixed support at point A, so definitely you will be having a vertical reaction force which is VA, and you will be having a moment MA as well. So this is the scenario, and when you separate it from by removing hinge, so you can see the force by the hinge on segment BC was upward. So here the force on this segment AB will be downward, and this will be equal to VB. Okay, so I will draw this clearly downward. So this is your segment AB. This is your point A, this is your point B. Here you have VB downward. At A you have a vertical reaction force which is VA. You have a moment which is MA, and there is a distributed load over the length of AB, which is equal to 4 kip per feet. And this length was A, which we are interested to find out. Now what we will do is that for finding this MA, what we are going to do is that we will section this beam at any length of X. Let this length is X. Okay, so this remaining length will be equal to X minus A. Here we are going to take out this portion for our analysis purpose, and we will calculate the moment for that moment equation. So when you section it, so the free body diagram will be like this. This is your point B having VB downward. There is a uniformly distributed load 4 kip per feet, and when you section it, so you will having a shear force V upward and a bending moment in this direction. And let this point is your K point, and this distance which we have taken is this X minus A. So we'll find the bending moment equation for this section AB, and then we will see what we will do. So we will apply sum of all moment about point K is equal to 0, and taking the counterclockwise moment as positive. Now what we will do is that we will convert this distributed load into point load, which will be equal to 4 into X minus A, and it will act at a distance of X by A divided by 2 on both sides. Clear? Either this or this, they will be same. Okay, so sum of all moment about point K is equal to 0. So this VB into perpendicular distance is X minus A, producing clockwise moment, so it will be negative. So I can write it VB into X minus A, that is clockwise, so it will be negative. Similarly, this 4 into X minus A, which is also producing clockwise movement, so minus 4 into X minus A into perpendicular distance is A minus A. Oh, 1 minute. So this is total A, and this distance is X, so this will be A minus X. So you should be very careful. So correct it. A minus X. Similarly, this is also A minus X. A minus X. A minus X. A minus X into A minus X divided by 2. And this moment, which is also clockwise, minus M is equal to 0. Now we know that VB is equal to 2B. So what we will do is that we will plug the value minus 2B into A minus X minus 4 into, this will be 2, because this will cancel with this 2. So 2 into A minus X whole square will be equal to this moment. And moment will be equal to minus 2 into A minus X whole square minus 2B into A minus X. Clear? Okay. So if we want to draw the bending moment diagram for this, so this is your VB, which was downward. There is a distributed load. All this thing I am doing is that I will tell you in a while why we are doing this. This is M and this is K, and this was your total distance A. Clear? And if you want to draw the bending moment diagram, so I will draw a vertical line from the end of the beam, and then we will draw a horizontal line to show the length X in meter. Okay, and we have moment for X. This is your equation number 2. For X is equal to 0. So if you plug X is equal to 0 in this equation, so what you will get is that M is equal to minus 2A square minus 2B into minus 2B into A. Okay, so minus 2A square minus 2, and B is equal to 18 minus A. Let me show you here B is equal to 18 minus A is equal to minus 2A square minus 36. Okay, what? And there is also A over here. Okay, minus 36A plus 2A square. So it will be cancelled, so minus 36. And you can see again that this is your moment at point A, which is equal to MA, because at X is equal to 0 we have, this is not 0, this is 36A. Okay, and minus 36A, minus 36A. Okay, and you can see that negative sign is downward, so I will write it like minus 36A. So moment at this point is this one. And for X is equal to how much? A. If you put X is equal to A in equation number 2, so you can just plug it in this. Where is the equation to this? So this A, X is equal to A, this term will be 0, and this term will be equal to 0, so moment will be equal to 0. So it means that your moment will be 0 at this point. And this moment, you can see this is a quadratic equation, and the curve will be like this. So the maximum bending moment, I will write it maximum. If I take the absolute value, so the maximum bending moment is equal to 36A, because taking the absolute of this value will give you 36A. And this is for segment AB. Now you have maximum bending moment for segment AB and maximum bending moment for BC and maximum moment for segment AB. If I join these two diagrams, so this will be like, it will be like this. This is the moment M. So for example, this is minus 36A. So this is your for segment AB, and for segment BC it was like that. If you remember, if you join this bending moment for AB and this bending moment for BC, so it will be like this. And here the maximum bending moment was B square over 2. B square over 2. Now we will start from here, and we are going to find out A, for which in question it is given that find A for which the absolute value of bending moment in the beam is as small as possible. And this is the condition. We can find it when you take the maximum bending moment for segment AB will be equal to maximum bending moment for segment BC. Why? You can see this is minus 36A and this is plus B square over 2. Now the bending moment here is, one is this maximum bending moment and other one is this bending moment. So if you make them both equal, so this will give you the condition which will be the minimum bending moment. So put the value of this. So this is 36A is equal to 1 over 2 B square. Okay, so we will put the value of 36A is equal to 1 over 2 and B is equal to 18 minus A whole square. So I will take it 36A is equal to 1 over 2 18 square plus A square minus 2 8s are 36, 36A. And again you can see this is when you solve this, this will give you 1 over 2 A square minus 54 times A plus 162 is equal to 0. So this is a quadratic equation, so we will find A, and this A will be equal to minus B plus minus B square minus 4AC divided by 2A, where A is equal to B is equal to minus 54, A is equal to 1 over 2 and C is equal to 162. So just plug in, you will get A is equal to 54 plus minus plus minus 50.9118, and you will, as A cannot be negative, so you have to take this A as A cannot. If you take two values, so plussing them, A is equal to 54 plus 50.9118, and that will be approximately equal to 104.9118 feet, which is not possible. Why? Because you can see the total length of this beam is 18 feet. So it's not correct. So other value of A is equal to 54 minus 50.9118, and that is equal to 3.0883 feet. So this is the value of A, 3.0883 feet, for which the absolute value of the bending moment is as minimum as possible. Now in part B, corresponding normal stress due to bending stress. So for part B, we know that corresponding normal stress is equal to maximum bending stress divided by the section modulus. So maximum bending moment is equal to how much? You can see here the maximum bending moment, both we have taken equal. So whatever you take, I will take this 36A. So 36A, and the value of A is 36 into 3.0883. That will give you how much? 111.179 unit will be kips into feet. And if you want to convert it into inch, so 111 multiplied by 179 kip multiplied by 12 inch, and that will give you 1334.15 kip into inch. This is the maximum bending, absolute value of bending moment. Now we'll need section modulus. So section modulus. So you can go to the end of the book where you have the section properties. So you have to look for this W14 by 68. Let me show you here W14 by 68. And you will take the value of S. Let me show you if I have this one. So you will go toward the end of the book. Section properties. Properties of roll steel. So where you have to check the US customary. W14 by 68. Okay. Now I have find it. Sorry. This is W14 by 68. And where will be the value of Sx? So you have to take this in this line. So W14 by 68. This is 77.8. So 77.8. Sorry, this is no. This is the line. This is 103, and the unit is cubic inch. So 103 cubic inch. Now you have both values, just plug in. So now maximum normal stress will be equal to 1334.15 kips into inch divided by 103 inch cube. So you will get 12.95 kip per square inch, and we can also call this as 12.95 KSI, because kips is kilo pound, so pound per square inch is PSI, and kilo is there, so it will be KSI. So one answer of part 1 is this one, and second is this one. Clear? And that was the solution or description of problem 5.28. I hope you have enjoyed this video and you have learned from it. It was on the request of one of my subscriber who asked me to record this video for his understanding. I hope you like it, and if you haven't subscribed my channel, then subscribe it, and don't forget to press the bell icon so that you can get notification about my latest videos. If you have any question, you can ask me in comment section. Thank you for watching.